morning. We have done the lumped mass system for modeling an explosion, and as per the theory what we developed, we found that there are two parameters which govern whether an explosion is possible or not. The first one is the ratio of the activation energy divided by the value of, let us say, the initial temperature. That means, this is so much joules per mole, this is also the ambient temperature T ambient into the universal gas constant, and the other parameter is the ratio of the heat released kg per mole divided by, we can say, the specific heat per mole, that means joule per mole Kelvin into T ambient. We said if both these parameters are large, an explosion is more likely. We said based on this, the activation energy must be large or the ambient temperature must be small. What does this non-dimensional term represent? It represented the tendency for spurting, that means a small value of the chemical energy release time. Rather, we said if I represent the chemical energy by the value of QC dot, that is dQ by dt, and if I put the time over here, well, initially the reaction takes some time to take place, but by the time the actual energy gets liberated, it is in the form of a spurt, and this happens when the value of the activation energy is large. Equivalently, when I say, well, if the activation energy is large, I have this spurting technique and the actual time of chemical reaction is therefore a small value. Well, I say this is the chemical reaction time, this is the induction time Td, and therefore, any explosion is associated with a small value of the chemical reaction time compared to the heat release time, which we have seen in detail in the last class. Therefore, what is this? Therefore, activation energy must be large. We said for most explosives the value is around 80,000 to 160,000 joules per mole. The second point is, if the ambient temperature is high, what is going to happen? If the ambient temperature is high, well, the reaction starts off, because the ambient temperature is high, the reaction starts off at a fast rate, and therefore, the spurting tendency gets diminished. Therefore, an explosion is more likely when the ambient temperature is small. Now, this is the non-dimensional parameter which characterizes the spurt in chemical reactions or spurt in heat release after an induction time. This term just tells you what is the magnitude of heat release vis-a-vis the initial internal energy of the medium. If I have more energy release, well, an explosion is capable of forming a strong blast wave. These are the two parameters. What I do in the class today is, maybe we will try to apply it for different chemical reactions, one or two typical cases or maybe one typical case, such that we know how to apply it. Like for instance, let us go back to our starting point. We always took this example. We said, well, I have a container. In this container, I have hydrogen gas, I have oxygen gas, which are mixed together. We told, well, hydrogen and oxygen can be in the container for years together. Let us say it is at room temperature, it is at, let us say, 30 degrees centigrade, which is the room temperature. It can be there at 30 degrees, let us say 1 atmosphere pressure for years together, nothing is going to happen. But if I want to start a reaction, we said, well, I must put an electrical spark in it. That means I deposit some energy at some point and maybe the reaction takes place. I am still within the confinement of overall what we said is uniform temperature, uniform concentration. Therefore, I am still looking at the lump parameter approach. I put some energy release, and what does the energy release do? It takes the hydrogen, maybe the hydrogen takes place. It decomposes the hydrogen or it breaks the hydrogen into H and H atoms 0.1. It could, because I am releasing some energy, I have hydrogen and oxygen, maybe it breaks it up into H and H atoms, we will see what this is. It also takes the oxygen molecules and breaks it up into O and O atoms, and also maybe the hydrogen and oxygen, since they are mixed together, it could also break it up into hydroxyl OH and OH atoms. Now, the H atom, O atom, OH atom are all active, see, this is something which is nascent stage. Therefore, these are all active radicals and these are known as chains. That means what you do is active chains. Therefore, what we do is the act of putting some energy release in it activates the hydrogen molecule into hydrogen chain, H chain, O chain and OH chains. And therefore, these three reactions I can call as, let us say, the chain initiation or active radical. That is, I say, well, I have chain initiation which takes place when some energy is released into the medium. I have, let us say, OH being formed, it could react with H2 and what could happen? I could form H2O and H2O and 1H. That means for every chain of OH, another chain of H is being formed. We call this as chain propagation. That means the chain continues to propagate. It is still possible that I can have maybe the hydrogen molecule which is available. When when one of the chains like O comes and reacts with it, I could form H and OH, and similarly I could also have maybe the O2 which reacts with the hydrogen chain which is formed here to form, let us say, OH and O plus OH. Therefore, in this case what happens? One chain or one O radical or one chain forms two chains over here. Therefore, we call it as chain branching. Therefore, what has happened? The act of releasing some energy starts these reactions, maybe the chain initiation reaction, chain propagation reaction, chain branching reactions, and what it does, it produces a lot of these chains. And you will recall, we also talked in terms of maybe that this axis represents the progress of a reaction. We said that the energy could be plotted on the y axis. Well, initially hydrogen and oxygen maybe at 25 degrees, it is at almost 0, maybe at 30 degrees the energy content is over here. And what happens? They act, I want to initiate the reaction, therefore, I put some energy, it gives some activation energy, takes it up to a transient stage over here, and then what happens? It reacts and forms the products and forms the product which is H2O, and we know that the heat of reaction of the products H2O, we will recall we had delta H2O, heat of formation under standard condition was something like minus 296 kilojoule per mole. Therefore, this corresponds to the product, maybe lower energy level, and therefore, this is the heat of reaction which is given, and therefore, and this is the activation energy. Therefore, what did activation energy do? When we want to activate a radical or a reaction, what we do is we are essentially forming these chain carriers, and therefore, what happens is I form all these chains which are in the transient state over here. That means I form H, I form O, I form OH. Because of this is formed, this is all not stable, it is all chains, all active radicals, and these things later on combine, and what happens? Let us put this maybe H plus let us say H may combine with OH to form maybe H2O, or let us say H plus OH, whenever it combines like this, maybe sometimes the third radical also influences this, but let us say, well, H and OH can combine to form a stable molecule, or rather I can also form H plus O2 also can combine, let us say HO2. But since these are all helped by the molecules which are available, that means molecules which help such a reaction to take place. Mind you, whenever we say chemical reactions, the H atom and O2 atom must hit against each other. If there are neighboring atoms which are also, or neighboring molecules which also help this hitting and breaking the structure, we call it as a third body. I can also write it as HO2 plus M. Similarly here, H plus OH giving H2O, I can write it as M, giving H2O plus M, I can form H2O by different means H2 plus O plus M. That is a third body. It could be OH, it could be H, it could be H2, it could be O2, which facilitates this reaction, giving me H2O plus M. Well, these are the recombination reactions. I say these are the recombination reactions. And when recombination reactions takes place, well, the H, O and OH which are formed here come back to the products, and I get the completed products of combustion. Therefore, we say, well, the reaction takes place through something like a chain initiation step followed by chain propagation and chain branching, and ultimately the energy is released in the recombination. Why did I say energy being released in the recombination? Maybe I have to look at these reactions a little more closely. Let us say what is the heat generated in this reaction, because ultimately let us not forget this, and what is it I am working towards? We want to find out whether this reaction between H2 and O2, I do not know the proportion, I presume it goes through these steps of reaction. As a function of time, if I were to plot the heat release, for an explosion to occur, I should have something like a phase during which not much energy is liberated in an induction period, followed by a spike, and this is what I expect in a chemical reaction to take place, and therefore, let us keep our tendency for this spiking, and therefore, maybe it spikes and then it drops off over here. Therefore, is it possible? How do I calculate this? Let us go back and see what is the heat release in these reactions. To be able to get the heat release, it is necessary for me to know the heat of formation of the reactants and heat of formation of the products. We tell ourselves, well, I go back to the literature and look at heat of formation. I find that the heat of formation under standard condition for H is equal to the value of heat of formation for H is equal to 218 plus 218 kilojoule per mole. The heat of formation of oxygen atoms, heat of formation standard for oxygen is equal to plus 248 and the heat of formation of OH is equal to plus 2, no, it is plus 39. Kilojoule per mole. You know, in other words, to form H, I have to supply heat. That means H2 has to be heated to form this. Therefore, the heat of formation of H atom, O atom, and OH over here, HF of OH are all positive, this being 39 and this. Using this, I can calculate the energy released in this reaction. If I were to put it just below this, what is the net value? Minus of heat of formation of H. Well, heat of formation of H is 218, I have 1 plus 1, 2 radicals, 2 into plus 218 minus H is a naturally occurring element, that means H occurs and it is at standard state minus 0. Therefore, the heat of formation of this is minus 436 kilojoules for this reaction. So, also for the reaction O2 is equal to O plus O, we have heat of formation of O is plus 248, therefore, it is minus of heat of formation of products, I have 2 of O, 2 into plus 248 minus, anyway O2 is 0, therefore, this is equal to minus 496 kilojoules. If I take a look at this reaction, these are stable things, I have OH over here, heat of formation is minus 2 into 39 minus 0, which is equal to minus, that is minus 78. In other words, kilojoules. In other words, the heat of reaction over here is minus 436 kilojoules, heat of the reaction O2 dissociating into O is minus 496, the heat of reaction is minus 78. That means, these reactions are endothermic, that means they absorb energy, no heat is being liberated in the 3 chain initiation reactions. If we take a look at the heat of reaction corresponding to OH plus H2 giving H2O plus H, what is it I get? Minus of H2O. Well, we know by now, yes, heat of formation of H2O, let us say heat of formation at standard condition for water as a liquid is equal to minus 295 kilojoules, 296 kilojoules per mole. Therefore, I put the value, I have 1 mole of this, therefore, 295 and the value of H is, but mind you, 295 it is minus, that means minus 295 plus H, that means H is positive plus 218, that is the value of the 2 products H2O and H, this is the heat, and for OH, well OH is minus 39 minus of plus 39, this is for the products. And if I add this up, the heat of reaction of this particular propagation reaction comes out to be equal to plus 28 kilojoules. Similarly, I can calculate the energy for the chain branching reactions. Now, I know the heat of formation of H, I know the heat of formation of OH, I know this, I put together. Similarly, I get the value for the chain branching reaction as H2 plus O giving me something like 70 kilojoules in a similar manner, and for the last one O2 plus H giving O plus H, the energy released in this reaction is 8 kilojoules. Well, we find yes, these two reactions and this one, these three, the chain propagation and the chain branching reactions are exothermic, but the exothermicity is small. How do I say it is small? Let us work out one or two cases. Let us find out the exothermicity of, let us say, a reaction like H2 plus O plus M is equal to H2O plus M. If I take this, well, the heat of this particular reaction is equal to minus of H2O, that is minus 285, and I have O over here. We know heat of formation of water is plus 248, therefore, I have minus 1 into 248. Therefore, the heat of this recombination reaction H2O plus H2 plus O plus M is equal to H2O plus M comes out to be something like plus 534 kilojoules. Similarly, if I were to write the heat of formation of this maybe H plus O2 plus M, HO2 plus M, we said, well, the heat of formation of HO2, if I go to the standard literature tables and plot it out, well, HO2 has a value of plus 2 kilojoule per mole, and therefore, the energy liberated in the reaction H2 plus H plus O2 plus M is equal to HO2 plus M is equal to, we are talking of maybe minus of plus 2, that is the product, we have 2, M and M is the same over here, minus I have H over here, the value of heat of formation of H is equal to plus 218 minus 218, which is equal to something like 216 plus, therefore, because this is a small positive value over here, it is plus 216 kilojoules. Therefore, these recombination reactions have high value of exothermic heat release, whereas the chain propagation and chain branching reactions have very small values 8 or 28 and all this, whereas the chain initiation reactions have hardly, they absorb energy, they are endothermic. Therefore, you know what is going to happen? Let us say I dump some energy, I start these chain initiation, chain propagation and chain branching reactions, and as more chains are being formed, I have the recombination reactions taking place, and what is it I find? I find, well, the energy is essentially liberated in the recombination reactions, and hardly any worthwhile energy gets liberated here, with the result what I can now tell is, well, during the initial phase of the reaction, when I activate the reactions, that means I look at maybe the temperature gain. What is going to happen? The temperature hardly changes, it just is endothermic, which is balanced by the energy release, and once the recombination reactions take place, the temperature increases and I have a signature like this. In other words, initially there is hardly any value of chemical heat release, and which is followed by a spurt. Therefore, in this period I have chains which are being formed, chains being initiated, followed by a period in which the chains recombine to give heat. Therefore, we tell ourselves, well, during the initial phase I have chain initiation, chain propagation and chain branching reactions, that means initiation, propagation and branching reactions for the chains, and the chains combine in the period later on to give energy, that means Tc corresponds to recombination, and during the initial phase I just do not get much energy release. Well, this matches with whatever we were telling for high activation energy, and this is how a reaction progresses in practice. Having studied this, you know, why are we going into these details? See, tomorrow we want to control a reaction. or control an explosion. If you want to control an explosion, it is necessary that I do not allow this to happen. Maybe I should somehow absorb the change during the reaction, and this is what I will do subsequently. But to be able to be clear on what little we have been doing so far, let us put it together in a plot of, let us say, the last plot could be maybe as a function of dt by dt, that is the rate of temperature rise, as can I work it out as a function of time, which means as a function of the temperature itself, because we said as time increases the temperature increases, therefore, as a function of time I could be able to do this. I want to take a look at this. Therefore, we again say, well, my constraints are the following. I also have a lumped mass system, I have a volume, I have a density of the explosive which is rho, the CV of the explosive, that is the specific heat of the explosive is CV. I have the ambient temperature T ambient, the temperature at any time is T, the initial temperature could have been T0. Well, what did we tell ourselves? Well, I have the mass of the system rho v into the specific heat, that is the thermal mass of the system, into I have dt by dt, which is, and this gives me the rate in so much kilograms or kilojoules per second or joules per second. And where does this come from? It comes from the rate of the reaction, that is so much moles per cc second, into the value of volume, that means moles per second, multiplied by Q, so much joules per mole, it also gives me joule per second, and this is what I am balancing. I want to see how the value of dt by dt, that is d capital T by d small t changes, and therefore, now I write the value for the reaction. I say, well, reaction given by ACN exponential minus activation energy by R0 T into I have V and Q over here. And you will also recall we had an expression for C, we derived one expression for C. We said, well, I can write the expression for C is equal to C0 into temperature maximum minus temperature at any point in time when the concentration is C divided by Tm minus the initial temperature. We plug this in and then we say we can get the value of dt by dt is equal to, well, in this particular expression V need not be taken into account. I have AQ over here, well, I have divided by rho CV, and then we have taken these terms over here. Therefore, now we have only the value of Cn, therefore, I can write C naught raised to the power n, where we are still considering an nth order reaction, or we say the rate of a reaction is proportional to C to the power n could be 1, it could be even 0, it could be 2 for a second order reaction, and we said most of the reactions are n is equal to 2, and we said is equal to Tm minus T divided by Tm minus T0 to the power n A C0 into we have the exponential term coming over here minus Ea by R0 into T into the value of Q over here. Well, this gives me the expression for the rate of temperature increase. And if I look at the rate of temperature increase, and let us say I first plot it with respect to temperature, that means on the x axis I have temperature, what is it I get? Well, when the temperature is initially, let us say the ambient temperature, I have Tm minus T0, Tm minus T0, well, this is a strong term, well, it is a small number over here, and as temperature increases and reaches the final maximum value, it becomes 0, that means ultimately it becomes 0 over here. And in between, if my activation energy is large, like what we have been talking earlier, well, the temperature increase is like this. It goes after a long induction time. Let's put it down more reasonably. We tell ourselves initially the temperature increase is small because the activation energy Ea controls it. After some time, well, it peaks like this and it comes down to 0 over here. This is the type of dt over d time curve. And what is the temperature? How does it change? Well, initially the temperature is T naught over here, that is, and it reaches the value, and therefore, if I were to now change this x axis, instead of temperature I plot the time, what is the type of relation what I get? Let us put everything together such that we can now interpret the reaction taking place and the rate at which the temperature build up takes place. I have temperature versus time, I have dt by dt. I want to plot it on the axis again. I also want to plot C as a function of time. Well, let us first plot this. Well, it starts with a temperature T naught and it goes to a maximum value Tm. This is the value of T. Let us now plot the value of the rate of temperature increase. Well, it starts at a low value, maybe somewhere over here the peak occurs. Well, it goes like this, peak occurs and comes back over here. This is the value of dt by dt. If I were to plot the concentration and if I denote the concentration C at any time, well, initially the concentration is C naught, the final value of concentration is 0 because all the fuel is consumed, and therefore, maybe this is initial value, it starts like this and comes over here. Well, these are the concentration plots, the temperature increase plots, the rate of temperature increase plots, and we tell ourselves, well, based on whatever we have discussed for hydrogen, oxygen, and it is true for any hydrocarbon or most of the substances, we can tell ourselves it is during this period that the chain initiation, chain propagation and the chain branching reactions are there and avalanche of chains are being formed, and these during this period recombination reactions take place during the actual time of heat release, that is recombination of chains to give me the heat, and these are essentially the chain formation stage. We should know, hey, what must I do to control? Supposing I do not want an explosion and all of us are looking at ways to control an explosion or to stop an explosion, what must I do to stop the chains being formed? Maybe I should add something such that the chains do not get formed. But before I do this, let us quickly take a look at the chain initiation reactions. We told ourselves, well, H2 forms H plus H. You know, the formation of chains is sort of facilitated when I have other molecules. Maybe I have something like maybe a wall, maybe I have something like an energetic wall which can help in the reaction, or I have maybe the oxygen molecule also provides a collision. Therefore, we say the third body helps in the reaction, and this third body does not take part in a reaction. It helps in the reaction, but it is available to me after the reaction as the third body itself. Therefore, we say H2 plus M is equal to H plus M, and the rate of a reaction we called as omega, so much moles per cc second, and that is equal to 2.08 into 10 to the power 15 exponential, the way we have been telling. Second order reaction, therefore, concentration of hydrogen into concentration of whatever is available as a third body over here. We also find that there is a weak dependence on temperature coming over here. You will recall when I got the value of omega, I did say, well, it could be a small function of temperature, and when we do experiments, we do find it is a weak function of temperature. In addition to temperature coming in the exponential term, we do have temperature coming over here. Similarly, the chain initiation reaction of O2 forming O plus O chains is also held by a third molecule, and the rate of reaction is given by, in this case again, temperature is quite weak over here, explicitly a combination of the oxygen and the third molecule over here. This is the reaction rate over here. Similarly, for the you also could have chain initiation reaction in which I have H2 plus O2 forming OH plus H. This is also chain initiation. Well, in this case, the temperature effect is not there. The rate of reaction is given by this. Knowing the rate at which the chains are there, I can write the value of omega is equal to d of H2 by dt is equal to omega into, using the law of mass action, as concentration of H into concentration of the third body. I can solve for the rate at which the chains are being formed. That means the rate at which H2 is getting depleted, or dH by dt is equal to omega into H2 plus M over here, and of course, I have two of them. Therefore, 2 of dH by dt is equal to this, and therefore, I can find out the rate at which the chains are being formed. This is for the chain initiation reactions. I get a similar one for the chain propagation reaction. OH plus H2 is equal to H plus H2O. The rate of a reaction is given in terms of the concentration of OH and H2, and we have the rate of a reaction is there. Similarly, the chain branching reactions H plus O2 giving OH plus O, and the chain branching reaction, that means for each chain I form 2 more chains, or O plus H2 forming 2 more chains, the reaction rates are given by this. These are somewhat temperature dependent reactions, in addition to temperature coming under the exponential sign over here. Therefore, we have the chain initiation, chain propagation, chain branching reactions, and when we talk in terms of chain termination reactions, I write these two, H plus O2 plus a third body. Mind you, when we talk of these recombinations and a third body over here, the collisions, you need a number of H, number of O2, because 3 bodies are reacting together at a point. This happens essentially at high pressures, because at low pressures, you do not have the feasibility of 3 molecules colliding with each other. Therefore, these 3 body reactions essentially happens at higher pressures, and we have HO2 plus M, we have H plus OH plus M giving H2O plus M, and the rate constants of these two are given by this. And we just now showed on the board that the energy release in these chain termination reactions are very much greater than the endothermic heat release or the energy absorption in the chain initiation, and the small values of energy released in the chain propagation and the chain termination reactions. Therefore, it is possible for us, using these known values of experimentally determined rate constants or the rate of a reaction, to be able to plot, to be able to determine the values of, let us say, H and OH and let us say O, which are being formed in the reactions, and find out the period or the time duration during which the chain initiation takes place and the recombination reactions take place. Having said this, let us come back and take one last look at the chemical explosions from the point of view of the following. Well, we said, well, hydrogen, oxygen, we will stick to this because it is quite illustrative. We said, well, I have, let us say, hydrogen and oxygen which is available. Can I say, well, all along, for all conditions of pressure and temperature, that means I want to take a look at the explosion diagram for pressure as a function of temperature. In other words, I have a mixture of hydrogen and oxygen in a container. I have hydrogen and oxygen. Let us say I vary the pressure and temperature. I want to find out, well, does the reaction, does the explosion diagram look quite the same for all pressures and temperatures? Or are there some regions of pressure and temperature in which no explosion is possible? Are there some regions of pressure and temperature in which explosion is possible? And that is what I want to take a look. Therefore, we just do whatever little we have discussed so far. Let us say I am interested in pressure. Let's consider a pressure limit of, let us say, 10 kPa, which is, let us say, 0.1 of an atmosphere. And let us consider a temperature region. Let's now restrict ourselves to a temperature region around, let us say, 500 degrees centigrade, or let us say 400 degrees centigrade, because you will recall we said that the auto ignition temperature of hydrogen oxygen mixture is around 440 degrees centigrade or so. Therefore, let's keep this in mind. Let us say in Kelvin, I am interested in a temperature of around, let us say, 700 Kelvin. This is my region of interest which I am looking at. Therefore, if I am basically interested in the low pressure region, that is subatmospheric pressures, that is I am interested in this particular region, can I say under what conditions will an explosion occur in this particular region? Well, I know that when the pressure is large, that means when pressure is large, that is of the order of, let us say, somewhere over here around 8 or 10 kPa, pressure is large, therefore, the collisions between the molecules H2 and O will be higher, and therefore, we expect more chains to be created when the pressure is higher. When the pressure is lower, well, no chains are created, but if the temperature is higher, well, the molecules have higher energy, and therefore, I can say chains will be formed something like this. That means, when I talk of very low pressures and high temperatures, I can say, well, chains are created in this particular region. That means, more chains are possible in this region. As the pressure is increases at lower temperature, more chains are being formed, and therefore, I tell myself this is the region in which more chains are being formed, and therefore, this corresponds to a lot of chains, and these chains can recombine and generate heat. Therefore, this shaded region, that is the hatch region, corresponds to an explosion. In this region, what is happening? Some chains are definitely formed, but they go back, they are absorbed by the wall because the chains are so few, and therefore, this region corresponds to no explosion. This is in the region of subatmospheric pressures. Let us now increase the pressure and still discuss this diagram further. Now, in the region, let us say I go to something like 100 kilo, or let us say, yeah, let us say I go to 100 kilopascal or a little higher, let us say 200 kilopascal. Then what is going to happen? You know, in this region, well, chains are being formed, but we also found that the reaction H plus O2 plus M forms something like HO2 plus M, which does not really give that much of heat, but what happens? The chain H gets consumed, and maybe at higher pressure and higher temperature, more and more chains are getting consumed and HO2 is being formed, and HO2, you know, is something which can be kept as it is for some amount of time. That means, at intermediate pressures and temperatures, it can form products, and therefore, this fellow continues to form HO2, that is, the chains get depleted here. We also find, yes, at higher pressures, more and more of these things are getting formed, chains are getting consumed. Therefore, I can think in terms of a situation something like this, wherein maybe if the pressure exceeds this limit, well, the chain gets consumed here. Since chain gets consumed over here, no explosion is possible in this region. That means, I put the graph over here, I say in this region no explosion is possible, but in this particular region, well, I have the chains which are being formed and recombination reaction generates heat, but in this region pressure is high, as temperature increases this reaction takes place, no explosion is possible, and ultimately therefore, I say, well, this is one limit wherein no explosion, and in this region I have explosion taking place. And now, if I increase the pressure still further, what happens? Well, I have HO2 being formed, and this HO2 can react with H2 to form H2O2 plus hydrogen. That means, chain is getting formed again, and this H2O2, I am sorry, HO2 plus H2, H2O2 plus H over here, and the H2O2 can again at high pressures hit against each other and form OH plus H. Therefore, at very high pressures, I again start getting the chain carriers which can produce a lot of chains, and these chains can combine to recombine to form heat release like H2 plus O giving H2O, or H plus 2H plus O giving me water, and therefore, the curve goes back over here. Therefore, in this case I have explosion taking place over here, and in this continues over here, no explosion. Therefore, what is it I see? Well, this corresponds to the second phase wherein the chain termination reaction is not allowing the chains to take place, and I have no explosion over here, but however, I get an explosion here, I have no explosion here, no explosion here. Beyond a certain value of pressure, I do get an explosion coming over here, and therefore, this gives me an explosion diagram. This is the limit where we say is the first explosion limit, wherein the vessel absorbs the hydrogen and I have no explosion. In this case, I have the chain termination reaction H plus O2 plus M, which absorbs all the chains and does not allow an explosion to take place. And well, in the third one, well, because of the high pressure effects, more and more chains are being formed, I have an explosion taking place. This is the explosion diagram, and this is called the third one, wherein I form chains readily. I illustrate this in one of the slides which I will show now, and what is it we see in this particular slide? I just show the 3 explosion limits. Well, this is the first explosion limit at low pressures. This is the second explosion limit wherein the chain termination reaction robs of the chains over here, and I have at the higher pressures the third explosion limit. Therefore, we have a first explosion limit. Only on the right side, which is shaded, you have explosions. You do not have explosion in this particular region over here. And this is how we interpret explosions for the different explosives. Well, this is all about it. Let's spend a couple of minutes on what I told earlier, namely we wanted to find out whether I can control my explosion. Supposing I do not want an explosion, what is it I do? Let's see what could be done. In other words, I want to do something to my explosive. Let's again get back to the starting point, namely I have a vessel, let us say I have a container containing hydrogen and oxygen. Now, to prevent an explosion, I must not allow my chains H, OH, maybe O to sort of increase in large number, and these chains should not react and form the chain termination reactions or give a spurt in energy release. In other words, I want to control such that I do not create these chains at all, and for this what is it we do? Well, we use some substances which are like methyl bromide, we say CH3 methyl bromide, we say methyl iodide, or we say methyl chloride CH3Cl. These are halogen based compounds. They can in general be denoted by Rx, where X is the halogen and R is the organic radical. The halogen compound Rx reacts with the chain carrier H, that means it is robbing the chain carrier from the explosion, forming HX, that is the hydrogen halide and the organic radical. To be more clear about this, let us take the specific example of, let us say, a bromine compound. That means we are talking in terms of R, halide being bromine, RBr. The RBr reacts with hydrogen, that is the hydrogen chain, to form R plus hydrogen bromide. This hydrogen bromide so formed reacts with more of the hydrogen chain, that means it absorbs or robs more of the hydrogen chain from the reaction to form hydrogen molecule plus the bromine atom, and therefore, now we have effectively taken out H from the reaction, that is the chain carrier from the reaction. The bromine ions act with bromine ions to form the bromine molecule. That happens in the presence of the third body, that means the other atoms and molecules in the reaction, and therefore, bromine forms the bromine molecule, and the bromine molecule further reacts with the hydrogen atom, that is the hydrogen chains, to form hydrogen bromide and bromine atom. And now what is happening is, you are again robbing hydrogen from the reaction or from the explosion, that is the chain carriers are being further removed, and this bromine atom again robs further chains of H to form H plus Br in the presence of the third body to form hydrogen bromide. Therefore, you see a series of steps by which the hydrogen chain carrier is being removed, and also we find, well, hydrogen bromine also or hydrogen bromide gets further regenerated in the reaction, which effectively promotes further robbing of the chain carriers. Therefore, the regeneration of HBr effectively removes the chain carrier H, and in this way you are removing the chain carriers, and when we remove the chain carriers, well, you do not have much of the chain carriers to prolong your induction time and also accumulate chain carriers by which you have a spurt or a peaking in the reaction. In the absence of chain carriers, therefore, you do not therefore get an explosion, namely a long induction time followed by the spurt in the reaction, and this is how the halogen compounds like Rx are effective in removing the chain carriers and inhibiting the chemical reaction, which could lead to an explosion. We must remember that phosphorus compounds similarly react with chain carriers and eliminate them, and therefore also inhibit the explosion process. You use phosphorus compounds, and these phosphorus compounds could be mono, ammonium phosphate, the formula being NH4 H2 PO4 and the second being trisodium phosphate. Formula being Na3PO4. Therefore, adding such inhibitors to our explosive substances will arrest the formation of chains and will not allow the explosion to occur. Well, this is all about the theory of explosions, and it is time we go to the next chapter, but before I do that, let us take one small model problem such that we revise the total what little we have done. You remember we talked in terms of different types of explosions, and I think it is necessary for me to tell one last thing. Supposing let us say I have a leak of let us say propane C3H8, or let us say I have a leak of methane such as it happened in Ural Mountains in 1989, in which I formed a huge cloud of methane air mixture because of some pipeline burst. And supposing let us say I have this methane air which is accumulated as a huge cloud. Mind you, this cloud is at atmospheric pressure, the ambient is also 1 atmosphere pressure, therefore, it is just an unconfined cloud as it were. It is not that I have a container or a bomb in which this particular gas mixture is available. I can understand when I contain a mixture in a bomb, well, pressure builds up and the bomb bursts, but this is in atmosphere itself. In atmosphere itself, supposing I have a cloud of methane or a cloud of propane with air which is formed, can it result in an explosion? The question is, well, it is not confined, but I do realize that maybe propane, methane or hydrogen cloud goes through the process of having, let us say I plot it now, the heat release from this particular cloud. What happens? Initially I have an induction time, followed by induction time I have a spurt in the energy release. Because I have this spurt in energy release after this induction time, and this chemical reaction time during which actual heat release takes place is very small, what happens is because of the spurt, blast waves are generated and you can have an explosion even in an unconfined environment. It is not necessary that I put my explosive only in a bomb or in a container and have an explosion. It is possible to have unconfined explosions, and this is what we will be considering subsequently. We will talk in terms of confined explosions, and we find even in unconfined conditions, that is open unconfined, it is possible to have an explosion. Let me quickly go through one last example, maybe a worked out problem in which I will now consider maybe the example of the Texas City disaster. We have done this problem already for the heat release. What did we say? In the case of the Texas City disaster, we have ammonium nitrate, and this ammonium nitrate was contained in bags, several bags of them, something like 7,700 tons of ammonium nitrate. This happened in 1947. And what is there? You have the hull of the ship in which all these bags of ammonium perchlorate ammonium nitrate were all packed one against the other. This represented something like a well insulated system and little bit of energy release. We said, well, under all conditions I can have some, even at room temperature, some element of chemical reaction takes place. There is a small amount of temperature increase taking place, and therefore, the small amount of temperature led to higher and higher temperatures and higher energy release, and it resulted in a very drastic explosion. Now, I want to find out what is the preheat required to cause this explosion. When we look at ammonium nitrate, well, from literature I know that the activation energy is something like 90,000 joules per mole, and therefore, we will say let on that day explosion occurred, let the temperature be 30 degrees centigrade. Therefore, now I know from what we studied is Tc, that is the critical temperature minus T ambient, is equal to, we have the value of R naught T ambient squared divided by the activation energy, and therefore, I get the value of the critical temperature minus the ambient temperature as equal to 8 universal gas constant into T ambient. T ambient is 30, that is equal to 303 Kelvin divided by 90,000, and this number works out to be equal to 8.48 Kelvin degree centigrade. Therefore, the value of the critical temperature is equal to something like 30, that is equal to 38.48 degree centigrade. You find that the preheat temperatures are still small. The critical temperature is 38.48, which in Kelvin comes out to be equal to plus 273 is equal to the value is 311.48 Kelvin. I add 273 to it. Now, I want to find out the rate at which energy gets liberated, and we told yes, I must evaluate it at Tc, and there are some experiments which are conducted on the rate of reaction for ammonium nitrate, and it has been shown by Hainer in one of the combustion symposiums that the rate of reaction of ammonium nitrate is given by 10 to the power 13.8 into exponential of minus 80,000 divided by R naught T second inverse. That means, it is something in which even the concentration is not playing a role, it is this is the rate of a reaction, and therefore, how do we evaluate the heat release? We find out the rate of a reaction under the critical condition, that is Tc, that means temperature is going to be 311.48. We evaluate so much second inverse. We already know if I have ammonium nitrate how much energy is liberated. We say well NH4 NO3, we have the products, we find out the heat of formation of the products minus heat of formation of reactants. We know what is the energy which is liberated per unit mass. Therefore, for 7,700 tons what is the energy which is liberated, and this energy liberated into the rate at which it is being liberated, so much per second, that is second inverse, gives me the rate at which energy gets liberated in this particular reaction. And we find that the time constant of this at Tc is a small number compared to the heat characteristic time, and therefore, the explosion takes place. This is how we do any problem relating to an explosion. Well, this is all about the theory for explosions, but mind you, we have made a drastic assumption. The assumption is we assume a lumped mass system for the explosive. In the next series of classes, we will try to see what is the effect of this lumped mass system and whether we can really remove this assumption and proceed to interpret an explosion, and then we go back and look at confined and unconfined explosions. Well, thank you. An announcement, please. In the lectures 13 to 19, the energy release, rate of energy release and the thermal theory for explosions have been covered in detail. References for further reading connected with these lectures, namely 13 to 19, and a set of homework problems are given in the downloads of this video course.